Okay. So, here we go. If f of x equals the integral from 0 to g of x of 1 over the square root of 1 plus t cubed dt, and g of x equals the integral from 0 to cosine x of 1 plus sine of t squared dt, we want to find f prime of pi over 2. Okay. I want to find f prime of pi over 2. Now, so this is f. Let's just take a look at f for a minute. This is f, and we can find f prime using the fundamental theorem, right? But notice that f is a composite function. It's an integral for its outer function, and the inner function is g, right? Does that make sense? So the derivative of f prime of x, will be the integrand, which is this, evaluated at g, times the derivative of the inner function, which is g prime of x. Is that clear? Okay. We know what g of x is, so we can calculate g prime of x. Okay, so let's put this aside for now. Now let's look at g of x. G of x is also an integral, and we can calculate the derivative using fundamental theorem. Notice that the inner function is also is cosine x. So fundamental theorem says you basically just evaluate the integrand at the upper limit. So 1 plus sine, instead of t we want cosine. So cosine squared x. Then we multiply this whole thing by the derivative of that inner function, negative sine x. Okay? Alright, now we're specifically asked for f prime at when x is pi over 2. So I'm going to take that over here and just plug in pi over 2. So that would be the square root of 1 plus g of pi over 2 cubed times g prime of pi over 2. Okay? Just plug in x in that equation over there. So now g of pi over 2 is just a number, and g prime of pi over 2 is just a number. Let's figure out what those numbers are. First, let's look at g of pi over 2. G of pi over 2, basically replace x with pi over 2. You get integral from 0 to cosine pi over 2 of 1 plus sine of t squared dt. Cosine pi over 2 is what? 0. Well, this doesn't matter too much. This is just 0, right? So g of pi over 2 is 0. Now from here, we could figure out what g prime of pi over 2 is, because we need that in the answer. So replacing x with pi over 2, we have times negative sine of pi over 2. Okay? Cosine pi over 2 is 0. Sine of 0 is 0. So this bracket is 1. Sine of pi over 2 is 1. So 1 times negative 1. This is just negative 1. Okay? Great. Going back here now. f prime of pi over 2 is 1 over the square root of 1 plus g of pi over 2 cubed. Okay, g of pi over 2 is 0, so this is just 1 plus 0. Times g prime of pi over 2 was negative 1. So you get 1 over 1 times negative 1, which is negative 1. Okay? It's a good problem. It's using the fundamental theorem many times with the chain rule embedded in it. Any questions about this? So f of x is the integral from 0 to x of x squared sine t squared dt. And we'd like to find the derivative. Any ideas?
We should use product rule.
We have to do something before we could use the product rule. This isn't a product of two functions the way it's written. I'm sorry? Okay. The fundamental theorem says if this is a function in t, you could plug in x for t, right?
Okay. Can't you treat x as a dummy variable? Move it up.
You mean the constant?
Yeah.
Yeah. So as far as the integral is concerned, once x is chosen, this is just a number, right? It doesn't affect the way the integral is evaluated. So that's the first step we're talking about. You want to move that out. And then, what you said, use the product rule. This is a product of two functions. This is a function in x, and this is a function in x. So then the derivative is, the product rule says, it's the derivative of the first, keeping the second the same, plus keep the first function the same, and take the derivative of the second function. And the derivative of this is, of course, sine of x times x. Okay. Does that make sense? Okay. Great. This is just to whet our appetite for what's coming. The main problem I'd like to tackle today is this next one. Prove that if f is continuous, then the integral from 0 to x of f of u times x minus u du is equal to the integral from 0 to x of the integral from 0 to u of f of t dt du. Okay, this comes up in some physics problems. Okay. So let's think of how to begin. We can think about this as being a function in x, right? Does that make sense? And this is also a function in x. let's write that down. Let's say f of x is this first piece. And let's say g of x is the second piece. I'm asked to show that f is equal to g. We're just rewriting the problem. Okay? Does that make sense?
X minus u is actually dt.
No.
It's better to transform the left part.
Okay. How to transform the left part?
Separate first of all. Show as a sum of two integrals.
Very good.
And after, if we take the derivative, we can prove that left part equals to...
Okay, one thing at a time. So the first suggestion was to separate these integrals. That x minus u times f is xf minus uf, right? So we can separate the integrals and have two integrals like this. Okay? Using what we argued for the previous problem, I can pull this x out. However, uf of u du, right? But I couldn't pull this u out because it's the variable of integration. Okay. So anyway, so we rewrote f. Great, now we have to show that f is equal to g. Now somebody said something about derivatives. Right? Now, let's say we find the derivative of f. And we find the derivative of g. Okay? Let's say we do that. And then let's say that they're equal. That the derivatives of two functions are equal. Does that mean that the original functions are equal? No. What they differ by? A constant. Okay? Let's say we did that and the derivatives were equal. Then now we have that they differ by a constant, right? How would you say that those functions are equal if the constant is 0? Does that make sense? We're going on faith here. Okay? We're assuming we know how to do the derivatives. And then we're assuming that the derivatives end up being equal. And then from that we can conclude that the difference in the functions is a constant. If we can show that that constant is 0, then the difference in the functions is 0, which means the functions are equal. Okay? That's our plan, and let's see if it works. So we're going to start by taking the derivative of big F, which has two pieces. This piece is a product rule, okay? So the derivative of the first times keeping the second unchanged, plus the first times the derivative of the second, which is just f of x. Yes? Okay. Minus. Now let's do the derivative of this. Okay? And you might think this is the product rule, but it's not. This is just the fundamental theorem, direct application. So if you apply the fundamental theorem for this integral, what's the derivative? You replace every u by x, so x f of x, right? Okay, can we simplify this? These cancel, yes? And we just have integral from 0 to x of f of u b. That's the derivative of this function. Now let's take the derivative of g. Cross your fingers, we hope it's the same thing. Okay? Okay, let's go back here and look at this for a minute, okay? Okay. So we're saying that this is a function in x. And according to the fundamental theorem, we just remove the integral sign and replace the variable in the integrand by x. Now let's look at the integrand. The integrand is everything in this parentheses. Yes? And the variable is u. So if I were to take the derivative of this, I would basically just replace u by x and drop this integral sign. Yes? Great. So drop the integral sign and in the parentheses replace u with x. That's it. Okay? Does that make sense? It doesn't make sense. Okay. Let's write this as integral. Okay, I'm going to use some colors. Okay? Let's say that's the integral from 0 to x of, you understand this red part is a function of u, yes?
Yeah.
Okay, so let's call that h of u. D. Pick any letter you want. K of u. No. This part. This thing, yes, is a function of u. It's some function of u. So h of u, for us, it's that thing. 0 to u of f dt. Okay? Does that make sense now? Great. So then, what's the derivative of this integral? Just replace this with x. So it's h of x, right? What's h of x? 0 to x. That's why it's this. Okay? Are these the same? Yeah. T is a dummy variable. I could very well just say f of u b. Okay, so what is our conclusion? Therefore, so what we just saw that f prime of x equals g prime of x. Okay? We got the same thing. Alright? Alright. Therefore, from a theorem we got from the last chapter, they differ by a constant. Right? If they have the same derivative, they only differ by a constant. If I can show that this constant is 0, then their difference is 0, which means they are the same function, which is where we're headed at. Okay? Okay, now I'll stop writing, because okay. Anyway, let me not stop. Let me finish the story. So it's pretty actually. Well, it's both pretty and simple. Let's plug in x equals 0. Yes? So the argument is, if they differ by a constant for every x, then they differ by a constant when x is 0. The same constant, right? Okay. Because this is the same constant for every x we have. So then specifically, when x is 0, they differ by the same constant. Now, going back to f, let's look here for a second. What is f of 0? It's the integral from 0 to 0 of this garbage, right? Which is 0. Great. What is g of 0? It's the integral from 0 to 0 of this garbage. 0. So c is 0. Oh. Yes? So then f of x minus g of x is equal to 0. So f of x is equal to g of x, which is what we want to prove. Okay? This technique is very common for these types of problems. Right? So what type of problems? Problems where you have functions that you don't exactly can put your finger on because you can't integrate it, because you can't figure out what the integrated expression is. Then you have another function with the same problem. So it's very hard to say that they're equal. You can't perform any algebra. So then you say, okay, if their derivatives are the same, then I'm close to an answer. Okay? All right. Any questions about this?
What exactly did you do in that step over there?
Which step?
The second from the top.
This one? Product rule. This is the derivative of this. The first function is x, the second function is this integral.
I see.
Minus, this is the derivative of this. Okay? So this is not a product rule because it's just the integral of some function in u. Right? This is a function in x. Any other questions? Yes?
When you plug in 0 to like a function like that, it's always going to be 0, right?
Well, if the bottom part is 0, yeah. 0 to 0.
Exactly, so
If this is 1, then that's not the case. From 1 to 1, it's 0. Okie dokie. Thank you very much. We'll come back in 20 minutes. And we just proved that the integral from 0 to x of f of u times x minus u du is equal to the integral from 0 to x of the integral from 0 to u of f of t dt du. Right? So is that what we just did? Okay. Well, this is like the same thing. Instead of x, we have pi. And instead of f of u, we have sine u. So this is equal to the integral from 0 to pi of the integral from 0 to u of f. F is just sine, except it's evaluated at t dt times du. Right? Does that make sense? No. So replace x with pi, replace f with sine in this identity. Yes? Okay. Now, let's just do the parentheses. The parentheses, we're just integrating sine t from 0 to pi. Okay? The antiderivative of sine t is negative cosine t, and you want to integrate this, or evaluate this from 0 to pi. So, evaluated at pi, what do you get?
From 0 to u.
From 0 to u, negative. At u, you get negative cosine u minus negative cosine 0 du. So, integral from 0 to pi of negative cosine u plus 1 du. Right? Okay. And then you can integrate this. Antiderivative of negative cosine u is negative sine u, plus antiderivative for 1 is u from 0 to pi. So that tells you you want to evaluate this at pi minus, you want to evaluate this at 0. This is just 0. Sine pi is 0, so the answer is pi. Okay? It's just an application of the identity we just proved. Okay? So this identity we just proved transforms one integral into another, where the second one is easier to do than the first. Yes?
can I show you something that we wrote before?
Yeah.
Okay, before the previous one, we wrote the integral from 0 to x of u times f of u du is equal to negative x f of x? Like you plugged in x to...
When we were differentiating it, yeah. We were not differentiating. We know this formula. This formula always works as long as f is continuous. Okay? We're just using this formula. Our function f is sine. Our value for x is pi. So here we have pi. Here we have sine. Here we have pi. So on this case, instead of x we have pi. Instead of f we have sine. We're just using this formula. Okay, that's all. Because this is a pretty convoluted statement. Okay? I mean, the proof was interesting, but if we can't see an application, you might not see the value of it. This is pretty hard to integrate. Actually, based on what we know, it's impossible to integrate. So, I'm transforming it using this thing that we just spent so much time working on. Makes it much simpler. Okay?
Very nice proof.
Very nice proof.
Yes.
Thank you. Okay, all right, that's enough with the problems. Let's start the next chapter. This chapter is about applications of integration. Applications of integration. Okay. We're going to have some applications. We're going to have some geometric applications. We're going to have finding areas between curves. We're going to have finding volumes of solids. And then we're going to have some physical applications. Where we calculate work, where we calculate center of mass, and where we calculate pressure. Okay? And we're going to do that in that order. Today, we're going to try to talk about finding areas between curves. Okay? So here's a picture. Let's call this function f of x. Let's call this function g of x. We'd like to come up with a method that helps us find the area between these two curves and the vertical lines x equals a and x equals b. We'd like to find this area over here. Okay? We did this where the lower function was 0, but we just found the area under a curve and the x-axis. Okay? And the idea was that that's how we came up with integration. That was the whole point. Right? So we'd like to do something similar now. The idea from before is just estimate the area with rectangles and then let there be a lot of rectangles. So having said that, what we'd like to do is we'd like to cut up our interval. For each subinterval, we'd like to draw a rectangle that estimates the area in that region. And what we could do is we could take a point in that interval to represent how high my base is, the bottom of my rectangle, and how high the top of my rectangle is. So this is an example of a rectangle that estimates the area between the curves in this little region. And based on the second subinterval, I could do the same thing. I could pick a point that gives me the lowest and highest points of my rectangle and find the area there. And I can keep doing this. Okay, in this picture I'm just using the right-hand point of each subintegral, but you don't have to. Okay? Does that make sense? And if you keep doing this, then that gives you an estimate for the area between the curves f and g from A to B on the x-axis. Now, so let's say that the subintervals are of equal length. So instead of writing delta xk, I could just write delta x, because all the delta xk's are the same. Furthermore, let's call ck any point in the kth subinterval, x sub k minus 1, comma x sub k. Then I can extend this argument to say, let's say the first point represents x sub 0 and the last one represents x sub n. So I'm having n subintervals of equal length. Then an estimate for the area is the sum from k equals 1 to n. We're basically going to add the areas of each of these rectangles. Now, the height of each rectangle is the height that touches the top curve minus the height that touches the bottom curve. Okay? So what we'd like to do is, if you take this length, what is that length? If this point is c sub k, what is this point, the y value? F of c plus k. So this whole thing is f of c sub k, right? Now, if you measure from the x-axis to the bottom part, what is that? G of c sub k. Right? So then, how would you measure the height of the rectangle? Very good. So you get the area of one rectangle is going to be the height, which is f of c sub k minus g of c sub k, times the width. And the width of the rectangle is basically the width of the subinterval, right? Which is delta x. So this estimates the area between the curves f and g. Since the subintervals have equal length, I can just take the limit as n goes to infinity. Right? And what would this equal to? The integral of f of x minus g of x dx from a to b. Okay? That's what we cut out in subintervals, a to b. Okay? So this is the area between f of x and g of x and the lines x equals a, x equals b. Alright? And from the picture, we're assuming that f is greater or equal to g. Okay? Because otherwise, if I subtract g from f, and I want to make sure that the height is a positive number for the rectangle, so f must be more than g. If that's the case, then this is how we could find the area between the curves. Okay? So here is the first result. Let's go ahead and do an example. Find the area of the region bounded by curves y equals x squared plus 1, y equals 1 minus x squared, and the lines x equals negative 1, x equals 1. Okay? So find the area of the region bounded by the curves y equals x squared and y equals 1 minus x squared. The first thing you want to do when you're trying to find an area is draw the diagram that represents the area of the region. Draw the region. Okay. So in purple, we'll draw the graph of y equals x squared. Okay? So x squared plus 1, actually. So the vertex is here. There's a parabola that opens upwards. And the other curve, y equals 1 minus x squared. Again, the vertex is here, but it opens downwards. Okay? Now, we also have to graph the vertical lines, x equals negative 1 and x equals 1. So negative 1 is here, 1 is here, so that would be this vertical line and this vertical line. So the area of the region we're interested in is this region over here. Okay? It turns out that throughout this region, the purple function is higher than the orange function. So it satisfies that fact. So it's one way to look at it. Another way to look at it is to do this manually. I always recommend drawing a representative rectangle. A rectangle that represents the area of the part of the region. That way it's not hard to see that the height of this rectangle will be the y value of the purple function minus the y value of the orange function. So having said that, the area is equal to the integral from negative 1 to 1 of the top function minus the bottom function. Within that interval, that means x squared plus 1, that's my top function, minus 1 minus x squared. Okay. So if I integrate this and I get a number, that number represents the area of this region that I shaded. So let's simplify this first. If you simplify that, then you get 2x squared dx. Okay? So then the answer will be antiderivative, so 2 over 3x cubed from negative 1 to 1, and that would be 4/3. Okay? Yes?
Just for saying, like, can you, because it's symmetric over the y, can you just times it by 2?
Yeah. This is the same as twice the integral from 0 to 1 of 2x squared dx. Yes. You could see the symmetry from the picture. If you don't see the symmetry from the picture, you could see it here. This is an even function, right? And we're integrating over a symmetric interval. That's important. It's not enough that this is even, that this is symmetric about the origin. So that's why we could do this. Well, I guess it doesn't matter too much. The calculations aren't too bad here. Okay. Let's look at another one. Find the area of the region bounded by the curves, y equals 2x and y equals x squared minus 8. Okay. So again, we're going to start by, and we don't have any lines, we're just going to see if these two things found each other. So this problem is slightly different than the one previously, but the idea is the same. We don't have to come up with a new theory. So y equals to 2x basically is a line that has a slope of 2. So that's y equals to 2x. And then x squared minus 8 is a parabola that starts at negative 8 and opens upward. Right? Does that make sense? Okay, so if I were to draw this properly, what do you notice? Why don't we give vertical lines? Well, because these two curves basically touch each other twice, and they enclose a region. Yes? Okay. So then, naturally, I have an interval over which I want to integrate. And the interval depends on what these numbers are. This number over here, and this number over here. These numbers are the x-coordinates of the points of intersection of the two curves. Let's look for the points of intersection of the two curves. How do we do that? Okay, so we have x squared minus 2x minus 8 equals 0. Right? That means x minus 4 times x plus 2 equals 0. So x is negative 2, x is 4. Okay? What that tells us is that this number here is negative 2, and this number here is 4. Does that make sense? So that's the interval in which we want to draw rectangles and stuff. So if I draw a representative rectangle here, or anywhere else, I realize that throughout that region, and this is very important, okay, you'll see this in the next example, throughout the region negative 2 to 4, the line is always on top of the parabola. This is important for us to be able to use this idea over here. Okay? If I'm going to write an integral for the area between two curves, then we should have one function always on top of the other. Okay? Okay, anyway, let's see what happens here. So I have to set up this integral. So the area is going to be the integral from negative 2 to 4. Okay? Again, I want the top function minus the bottom function. The top function is 2x minus the bottom function is x squared minus 8. Okay? I can simplify this. 2x minus x squared plus 8. Okay, so this is just a polynomial with power, set of power functions, so we could integrate this using power rule. X squared minus x cubed over 3 plus 8x, and from negative 2 to 4. So then what we'd like to do is we'd like to evaluate this function at 4. It is 16 plus 64 over 3 plus 32. And then minus, evaluate the function at negative 2. This is minus 64 over 3, by the way. So that would be 4 plus 8 over 3 minus 16. Okay? Let's do the integers first. 16 minus 4 is 12. The 32 plus 16 is 48. 12 plus 48 is 60. Negative 64 minus 8 is negative 72. Divided by 3 is 24. So we get 60 minus 24. The answer is 36. If I did the math right. Okay? Okay, now, here's the thing. We're calculating area, which means your final answer must be positive. If you get a negative answer for the final area, or if you get 0, you clearly see that that region has to have a positive area, then you've made a mistake. So rethink what you've done. Okay? Does that make sense? Okay. Let's look at some other possibilities. Here's another one. Find an area of the region bounded by the curves. So here are the curves. Sine x and cosine x. And the lines x equals 0, x equals pi over 2. Okay? Again, if we write, here's what's going to happen. If we write the integral directly without taking anything into regard, we will get a wrong answer. What's the first thing we need to do here? Draw a picture. Yes? And our picture only has to go to pi over 2. So we can make the picture large. We know for both functions, the largest and smallest values are 1 and -1 respectively. So let's draw the sine x in purple. What happens from 0 to pi over 2? That's the highest point. So this is the graph and then it goes back down, right? Okay. What about for cosine? It starts at 1, right? And at pi over 2, what's the value? 0. Yes? So the region that we're interested in is between 0, the vertical line 0, and the vertical line at pi over 2. This actually goes all the way up. So the region we're interested in is this region over here, and this region over here. Now, if I draw a representative rectangle in this region, I notice that the orange function is on top. But if I draw a representative rectangle in this region, then I notice that the purple function is on top. So in that case, I can't calculate the area of this directly. I could calculate, I couldn't write a single integral to do this. I would have to calculate the area from here to here, whatever that is, and then calculate the area from here to here. Okay? Again, the rule we wrote over there depends on one function being higher than another throughout an interval. Okay? If they switch places as far as which one is on top within the interval, then I have to cut up the interval and take 2 intervals. Okay? Okay, so then the question is, what is this point? In this case, it's pretty easy. Right? In the first quadrant, the sine and cosine only meet at pi over 4. Yes? Okay, great. So then, what we do is, in that case, we'll call this area A1, and we'll call this area A2, and then we say, okay, the area that we're interested in is, we're first going to do A1, and then we're going to do A2, and then we're going to add, separate the problem into 2 other problems. A1 is a simple region, in the sense that one curve is always on top, and the other curve is always on the bottom. A2 is a simple region. But taken together, they're not simple regions, because the whole thing, they switch places. Okay? Each integral you write down, based on what we said earlier, has to be a simple region. Okay. Okay, so then let's write an integral to represent the A1 area. That integral spans the interval 0 to pi fourth. And within that interval, the top function is always which one? Cosine x. And the bottom function is sine x. That is A1. Plus, for A2, your interval is pi fourth to pi halves. And in that interval, the top is always sine x, and the bottom is cosine x. Is that clear?
Yeah.
Okay, and then we're gonna calculate these intervals. Let's see. Here, antiderivative of cosine is sine. Antiderivative of negative sine is cosine. And we're going to evaluate this from 0 to pi fourth. And then we're going to add the answer for this integral. Antiderivative for sine is negative cosine. Antiderivative of negative cosine is negative sine. And that's evaluated from pi fourth to pi halves. Okay. So we could do these calculations mentally. If I plug in pi fourth, this is half of square root 2, this is half of square root 2. So the total is square root 2. And then I take away, plugging in 0. That's 0, that's 1. So I take away 1. Okay? Plus, if I plug in pi halves, this is 0, and this is negative 1. Minus, if I plug in pi fourths, they're both half of square root 2. Negative square root 2. So they become negative square root 2. Okay? So then I would get 2 square root 2 minus 2 as the answer. See, you have 2 of these and 2 negative ones. Okay? Yes?
Okay, just like the previous one, I know this isn't from 0, but it's like pi over 4 is exactly between 0 and pi over 2. And so if the function is like, you know the rule where it goes from 0 to pi over 2 and pi over 2, it's like the same thing from 0 to pi over 4, except these functions are switched around. So can't you just, again, do 2 times one of the areas?
Not because of the reason you said, but because they are symmetric. Okay? But not because of the reason you said. Alright? It just so happens that those curves and those regions are actually the same, mirror images of one another. But that doesn't always happen. For example, if one of the curves was a cubic polynomial, that would be true.
Yeah, no, but like those integrals that you're evaluating, like they're
Even so.
if they're switched around,
Exactly, totally. Right? Because the way sine and cosine behave between 0 and pi over 4 is the same as they behave from pi over 4 to pi halves, as far as the change between them. Okay? But if one of the functions were different than sine or cosine, for example, if one of the functions was a cubic, that would be true. And you can see it from the picture, it would be symmetric. Okay? Alright. Now, let's take the possibility of having a picture like this. And we'd like to calculate the area of a region that looks like this. Okay? Where this is given by x equals f of y, and this is given by x equals g of y. Alright? Where this bottom part is the line y equals c, and this top part is the line y equals to d. Okay? In this case, you could think of this problem being the same problem as we did earlier, except it's kind of switched around. So I can no longer draw my rectangles vertically. Okay? Over here, it might seem harmless to draw the rectangle vertically. But if I go to this side a little bit, then my rectangles are kind of, this is the bottom, this is the top. You know what I mean? This is the bottom and this is the top. So and I get kind of several issues. So instead of doing that, what we do is we draw our rectangles horizontally. Okay? And we basically do the same type of Riemann sum we did. Instead of cutting the x-axis from A to B, we cut the y-axis from C to D. Now all we have to figure out is what is the area of one rectangle. If we could do one rectangle, then we could do many rectangles. Well, this is basically delta y. Instead of being delta x, it's delta y. So we got the width. Now let's get the length. Well, the length is going to be this x value minus this x value. Do you agree? Yes? Okay. What's this longer x value? F of y. What is the smaller x value? G of y. And if I subtract them, then I get the length of one rectangle, right? And if I do this for many rectangles, take the limit, I actually have this integral. So I won't develop the theory again. It's exactly the same thing. I have an integral in y now. And my interval of integration is in y, on the y-axis. And what's the lowest value? C to D. Okay? Again, this works provided that throughout the interval, the function that's to the right is always to the right of the other function. Throughout this interval. Okay? Again, if they switch places at any point, I have to take those sets of problems separately. All right? Okay, so let's take an example here. Enclosed by the line y equals x minus 1 and the parabola y squared equals 2x plus 6. Okay. All right, so we have to we have to graph this setup over here. Now, this one in pink is not hard to graph. It's a line through the point -1, 0 with positive slope, slope 1. Now the parabola, the quadratic is in y, so it's a parabola that opens left or right. In this case, it opens to the right, right? And actually, if I write this y minus 0 squared plus 2 equals 2 times x plus 3, then I can read the vertex very quickly. What's the vertex of this parabola? Minus 3, 0, right? So it's somewhere here. And it opens to the right. Yes? Okay? So, okay, now we have the region. Right? So that's the region. We'll figure out what these points are in a minute. But that's the region. The region will shade it. Looks like this. Just to show that the vertex is -3, 0. That's all. Now at first it seems that I could do this using the old method of top minus bottom. Well, I can, technically, I can do that for part of the problem. See, if I just consider, actually, if I just consider this part, from here onwards, then throughout that interval, whatever it is, the parabola is always on top and the line is always on the bottom, right? So if that were my region, I would be okay with that. However, so if I draw a representative rectangle, I could prove that. I could prove that any rectangle, the top is always the orange, the bottom is always the pink. If I go back, but I draw the rectangle here, I'll have a problem. But the top and bottom are the same curve, right? Okay, so that immediately tells me top-bottom business, which is an integration in x, is bad news. So now I have to go and try to do the horizontal bars. Okay, so the horizontal bars, again, I have to imagine some bars and make sure that what is to the right stays to the right, and what is to the left stays to the left throughout the region. So I draw one rectangle, and mentally I try to move this rectangle up and down throughout the region. Make sure whatever's to the right stays there, whatever's to the left stays there, and that's the case. And if we think of horizontal rectangles, the pink line is always to the right, and the orange line is always to the left, right? Even down here, right? So anywhere. So that tells me, okay, then I can integrate in y. Okay, and I could use what we said over there. Integral of the right function minus the left function. But I'd have to figure out the interval in y. And I would, since I don't have vertical or horizontal lines to cut off the regions, I'd have to actually figure out what these numbers are. Right? Does that make sense? Okay. That's one. Two, I have to make sure that this pink function is a function of y. Okay, something with y. Can I write, this is the graph of this equation. Can I solve for x here? Yeah, it's just y plus 1, right? So this is my function. Over there, this is my f of y. Could I do the same thing for the parabola? For the parabola, I could say, I can solve for x. It's pretty simple. It's 1/2 y squared minus 3. Okay? Does that make sense? Alright. So then I have a function in y. X as a function of y. Okay? And some people choose to write, and this makes it easier for them, they call this x right and x left. So you know what to minus what. X right minus x left. It's always the larger minus the smaller. Okay, so now let's set up, well, before the integral, we need the points of intersection here and here. We can find that the same way we did the other one. We just set those two expressions equal. So 1/2 y squared minus 3 equals y plus 1. Okay? Yes? Okay, so if you multiply this by 2 and set an expression equal to 0, then you get y squared minus 2y minus 8. Okay? I think. Which is lovely, because that's the quadratic we had earlier. So it's y minus, is this correct? Yeah. So that gives us the value y negative 2, y 4. That means this bottom number here is negative 2, and this top number here is 4. Great, so according to what we did earlier, it's the integral over the y-axis, so from negative 2 to 4, of the right function, which is y plus 1, minus the left function, which is 1/2 y squared minus 3. And we're integrating the y. Okay? And then we get integral from negative 2 to 4. We simplify this part. Okay, we somehow get y minus 1/2 y squared plus 4 dy. Or we just did 1 minus negative 3 is 4. Okay, so this is y squared over 2 minus 1/6 y cubed plus 4y from negative 2 to 4. Okay? So the answer turns out to be 18. Just plug in the values and subtract. Yes? Okay, so we had 5 goals. We had 2 goals for geometry, area and volume, and we had 3 goals for physics. We just did the first one today. On Thursday, we'll do some more. Okay? Thank you.